assorted other sources, mostly accreting white dwarfs actually. Thanks for having me. So today I'm going to be talking about ionizing sources in the old stellar populations of retired galaxies. In particular, I'm going to be fleshing out the discussion that was started yesterday in Murat's talk on the possible contribution, or not, of accreting white dwarfs to the ionizing continuum in these galaxies. Now just to set the groundwork a little bit, in early type galaxies, if you asked somebody decades ago, they would have said, no, there's no warm ionized interstellar medium. Of course, now we know better. And early type galaxies are commonly found to host extended low ionization emission line regions. And a lot of work has come out in the past few years making a pretty definitive case that it needs to be powered by some component of the stellar population. The most likely candidate, various uncertainties aside, being post-AGB stars. And I won't say too much more about this because Robert's going to talk about this in the next talk. Other sources have been considered amongst the stellar population, such as low-mass X-ray binaries, and found to be subdominant. But what about accreting white dwarfs? So, specifically what I'm talking about are white dwarfs which are accreting hydrogen-rich material from some main sequence or red giant companion, and growing in mass through steady nuclear burning of this material on their surfaces. Now these are thought to be a good candidate for the origin of type 1a supernovae because it gives a natural explanation for how you could grow a white dwarf up to the Chandrasekhar mass and trigger an explosion. But for our purposes, they're particularly interesting because with luminosities on the order of 10 to the 38 ergs per second, and temperatures in the range of 10 to the 5 to 10 to the 6 Kelvin, depending on detailed processes in the mass transfer phase, these should be incredibly powerful sources of ionizing radiation relative to anything else available in the old stellar population. Also, conveniently, their spectra are relatively well approximated by black bodies. This has been confirmed by detailed non-LTE calculations by Thomas Raukebaum and collaborators. Certainly good enough in the extreme ultraviolet for our purposes. Now, you can put one accreting white dwarf next to a post-AGB, and the accreting white dwarf looks really impressive, but what's really important, of course, is the relative luminosities of the two respective populations. Now, there are two ways we can estimate the total luminosity of the accreting white dwarf population. As a rough estimate, we can assume that this single degenerate scenario, single white dwarf, idea for the origin of type 1a supernovae holds. In this case, it's very easy to estimate the total luminosity, because whether a few white dwarfs accrete very quickly, or many accrete very slowly, a certain amount of mass needs to be accreted per unit of time in order to bring enough white dwarfs up to the Chandrasekhar mass to match the type 1a rate. And since their luminosity is almost entirely that of nuclear burning, this gives us an easy estimate for the total luminosity of the population, at least in an average sense. And you can also do the detailed, you can put all of our understanding of binary stellar evolution together, whatever we have, and try and do the detailed population synthesis calculations. I'll come back to that at the end. But first, to get a feeling for the kind of relative luminosities we're talking about, I think the easiest way to do it is to look at synthetic spectra. So here I've plotted, just from Bourgeois and Charlot, typically used, the ionizing continuum for 3, 6, and 10 gigayears. And of course, the most striking features are the remarkable consistency of the ionizing output. There's almost no evolution of time. And this sharp cutoff at the helium-2 ionization edge. This comes from also from detailed non-LTE atmospheric calculations from Thomas Raukebaum, the same group which showed us that there is no sharp cutoff at the helium-2 edge for accreting white dwarfs. So what I'll do is I'll take our estimate for the total luminosity of these sources from above, and just for simplicity of comparison here, I'll put them all at one temperature. We'll generalize it on the next slide. So what we have in the event that accreting white dwarfs really are the progenitors of type 1a supernovae stands in dramatic contrast to what we see from the post-AGBs. There's significant dramatic evolution with time. This just follows the type 1a supernova rate, which goes a little faster than 1 over t. And since we don't have this cutoff, we suddenly have a dramatic boost in the ionizing continuum past the helium-2 ionization edge, much harder spectra. So we can check if these are making an important contribution by looking at recombination lines of helium-2 in the optical. The strongest is 4686 line. So we can take our post-AGBs with different combinations of temperatures and mass accreted per white dwarf, and build and fit for the generic case the expected recombination line luminosity in 4686. We have an annoying dependency on the total mass of the galaxy and the gas covering fraction. We can get rid of these by normalizing to H beta, which is sensible. Now we have something which we can test against observations. And as a first check, I asked my good friend Jonas Johansson, also at the MBA, to stack retired galaxies in the SDSS. Since I only have 10 minutes, I won't go into too much detail, so we used selection criteria a little bit more conservative than Sid Fernandez. Jonas and Mark Sarzi were a little nervous about the transition to AGN. And we also make a redshift cut at the lower end to make sure we're actually not just sampling the nuclei, and at the upper end just because we get worse and worse signals and noise. And we can break these up into age bins, and what we find is a remarkably flat evolution in the helium-2 4686 to H beta ratio. Perfectly consistent with what we would expect for post-AGBs. That's another feather in the cap for that hypothesis. The black lines are models with a minimal set single degenerate scenario for two different assumptions about the star formation history to give us the same mean mean luminosity weighted age of the stellar population. Looking at the gas in elliptical galaxies, we can say something about binary stellar evolution. We can rule out accreting white dwarfs as the progenitors of type 1a supernovae. That, I think, is exciting. By process of elimination, that would seem to only leave us with double white dwarfs. The merger of binary white dwarfs is the only plausible candidate, but obviously this isn't proof of that. Also interesting, plotted in blue here, is what we expect from binary stellar population synthesis. It's a calculation I did with another student at the MBA, Hailiang Chen. And what we see is, again, we expect this dramatic evolution. Now, Murat mentioned earlier that yesterday that we also see this similar sort of trend for low mass X-ray binaries. That could mean there's something wrong with our observations, but that seems doubtful. My suspicion, and also doubtful that we would see the same problems in optical emission lines and in the X-ray with our observations. My suspicion is that something is wrong with our understanding of binary stellar population synthesis. Again, looking at the gas in early type galaxies, telling us something about the stellar population instead of trying to go the other way around. So I think this is really exciting. Unfortunately, I know there are some people in the room who would really like to add another hard ionizing source, but it doesn't look like it should be accreting white dwarfs. One thing that I promised Brent Groves I would put in here is a brief discussion, just a quick note on post-starburst galaxies. Since the total ionizing luminosity from single degenerate progenitors from accreting white dwarfs rises more or less as 1/2. There's probably a turnover. There has to be some kind of turnover here, but certainly from a couple hundred megayears up, this should be an extremely big problem for post-starburst galaxies. I mean, we should have equivalent widths for O2 that are an order of magnitude too high from the definition of post-starburst galaxies. Now, what would be really cool is to look at these in detail with IFU, and I can talk about that during lunch or the coffee break after this. But I'll end on my conclusions and summarize with one really key point, which is that looking at the gas in early type galaxies has told us something very important about stellar population. This is turning things around from the usual effort to try and understand the stellar population in order to understand what's going on with the gas. And of course, just looking at a big stacked sample is not enough in this day and age. We need to go in and do the integral field spectroscopy on individual galaxies in order to make sure everything checks out. I think I'm out of time, so I'll stop there.
Robert, can you come forward and set up in the meantime? Take questions? Yep.
Yeah.
So you want to predict this helium emission line, don't you need to assume also that something about the dust content that could destroy the ionizing radiation?
Yeah, so we tried adding in dust and it didn't make a strong difference. I can pull up my notes from the about a year ago and then talk about this offline. I'd have to look into it,
How
but it
do you
didn't
know
make a
that?
huge
Because
effect.
we just heard that it's extremely uncertain how much dust is around these objects.
Yeah. It's, well, around the
Around the
post-HEB stars.
post-HEB stars,
Yes,
yeah.
not for the accreting white dwarfs. They don't have.
That's true.
Yeah. I thought you were talking about dust within these diffuse gas clouds.
Yeah, I was. I confused myself
Yeah.
after that.
Okay, no problem.
Any other questions? Jay?
Did you also compute for bit neon 5?
Because
Because that does show up in some postcards, and it's never quite clear whether.
yeah,
it's
no, and there's some. I looked into that and I can't remember. I mean, the single degenerate scenario predicts a huge luminosity for that. It's not. I guarantee that the neon 5 luminosity is not nearly enough for that to be the case. But accreting white dwarfs at all being there would be interesting. Yeah.
Surface burning white dwarf produces gigantic fluid.
Yeah, exactly. And this would be really cool. So if we show that they're making an important contribution there.
So looking for that line, which is not hidden in an absorption.
Yeah, so I have another paper, actually, yeah. So in Woods and Gilpin, we talk about post-starburst gases. I also talk about all the emission lines besides helium-2, but I just don't have room for that.
Next question, Glenn?
Yeah, so could you go back to your proper average observation? So what,
Yeah, sure.
what was the red curve? Sorry, I probably missed that.
Sorry?
One slide further, so the rat curve
Oh.
showing there.
This is...
So in the
Next.
medium to
Next.
yeah.
Oh, the red curve. Yeah, the red curve is what we would get just from the BCO3 models.
Okay.
Yeah. Which might be right for the wrong reasons, but checks out.
That's very interesting. So that seems to fit together what the Type 1A supernova simulators also find, plus all the different observational constraints. However, there may be some subclasses of Type 1As that actually could be posed. So actually, what
So
fraction
if
of
you
Type
turn
1As?
this down to about 10% of the Type 1A rate, you
So
get
that's-
something roughly
So that's
consistent.
something which you still basically would say is consistent. with
Yeah,
this. Okay,
yeah.
interesting.
Although, really, this is an upper limit on the total luminosity, right? Because this is ignoring all the white dwarfs that don't make the Chandrasekhar mass, but still accrete, or whatever mass it really explodes at. I mean, there's some uncertainty there. So it's probably actually less than 10%. So it has to be.
Thanks, right?
Thanks.
Move on.